Hello everyone! So I'm going to be doing this video again because the first video did not quite have a good audio, okay? So I'm going to be telling you about explosions, which is another example of conservation of momentum, okay? So when I'm talking about explosions, it can be the explosion themselves or itself actually, or really just any two objects that move apart after initially being at rest. So they move up away from each other, they recoil from each other, and they are going to do it with equal and opposite momentum, okay? And this is because the momentum is conserved in an explosion or in any exercise where initially I have two objects that are stationary, like ice skaters, for example, and then they move away from each other. So they push away each other. I have a spring attaching two trolleys, and the spring is released, so the trolleys move away from each other. So any of these exercises, they are going to be examples of explosions, okay? So things move away from each other with equal and opposite momentum. And this is the explanation on why the momentum is equal and opposite. If I pick the formula for conservation of momentum, which is here, this one, I have that the mass 1 times the initial velocity of the first object plus the mass of the second object times the initial velocity of the second object needs to be equal to the mass of the first object times the final velocity of the first object plus the mass of the second object times the final velocity of the second object. If you don't know anything about this formula, go on my conservation of momentum video where I explain this and I also derive this formula. Now, initially, the objects are at rest, so that means that u1 and u2 are 0, and any number multiplied by 0 is going to give you 0. So I get at the start that 0 plus 0 equals m1 times v1 plus m2 times v2. So the initial momentum is 0 before the explosion or interaction. Then I can move this around. So I'm going to move everything that is about mass 1 or object 1 to the other sides. And I end up with mass 1 times velocity 1 equals minus mass 2 times velocity 2. This shows that my momentum is equal and opposite, okay? So I have an equal and opposite momentum. So that's what happens whenever you have two objects. They are first stationary and then they interact in such a way that they both move away from each other. Other conclusions that I can take, well, they go in opposite directions. I know that because I have this minus sign. Velocity is a vector, so that means that the direction counts, and momentum is mass times velocity, so it's a scalar times velocity. So if I have a negative velocity, then I have a negative momentum, and it means that this the momentum that is a vector, is going in the opposite direction, so the direction of the vector is opposite to when I have a positive sign in front of momentum, okay? So for object 1 I have a positive sign, object 2 I have a negative sign, so that means that the objects move in opposite directions. Another conclusion that I can take is that if object 1 travels twice as far as object 2, then it must be that the mass of the object 1 is half of the mass of object 2. And I know that because if I want to see how far they travel, I calculate the distance. And distance by definition is velocity times the time. Now, the time that I have is the same because I'm thinking about the same interaction. So that means that my velocity is going to be the same as the ratio as my distance is going to be the same as the ratio of my velocity. So the ratio of distances is the same as the ratio of velocities. So if I go here and I divide v2 by v1, so v1 goes on this side, I get that this is equal to m1 divided by m2. So that means that if I have half of the mass, then my velocity is going to be twice as big, and therefore my distance traveled within the same time is twice as much. And I have here an example to show you. So again, here they say explosion, although it's two trolleys that move away from each other because of a spring, for example. And I have that the mass of the first trolley is 1 kilograms, the mass of the second trolley is 0.5 kilograms, velocity 1 for the first trolley after the interaction is 2 meters per second, and I want to know the final velocity of the second trolley. So I go on and I pick the formula of conservation of momentum and I substitute the values. So mass 1 times velocity 1 in the beginning plus mass 2 times velocity 2 in the beginning equals mass 1 times velocity 1 at the end plus mass 2 times the velocity 2 at the end. In the beginning, the two trolleys are stationary, so their velocities are 0, so multiplying a mass by 0 gives me 0, so I get initially a momentum that is 0 plus 0, which is equal to 0. Second part, mass 1 kilogram, velocity 1, 2 meters per second, plus mass 2, 0.5 kilograms, so half of mass 1. V2, the thing that I want to know. I forgot the word now. The subject, not the subject, but is the one that I want to know. So 1 times 2 is 2. I move the 2 on the other side, so minus 2 equals 0.5 V. So now I can calculate V by doing 0.2 divided by 0.5. I get a minus sign, and then 2 divided by 0.5 gives me 4. So that means that the final velocity for object 2 is 4 meters per second, which happens to be twice as much as the final velocity for object 1 that has twice as much mass. So as you can see, the bigger the mass, or if the mass is twice as big, they are going to have half of that velocity, and that means that in a certain amount of time, so per second, they are going to travel half as much. So 4 meters per second when they have half of the mass, and then half of that, so 2 meters per second if they have double the mass, okay? In this case, I am assuming that the kinetic energy of the two trolleys immediately after they separate from each other is equal to the energy that was stored initially in the spring, okay, when it was compressed. Now, in reality, in a real explosion or explosion-like exercises, the object's total kinetic energy immediately after the explosion, and again, explosion-like exercises, is less than the original total energy. So chemical energy, for example, in an explosion, it could be any other, the spring energy, so the elastic energy, okay? So is less, the energy after is less than the original energy because some energy is going to be transferred into a non-useful form, so into waste energy. So some energy will be transferred into heat, light, and sound energies, okay? Alright, so that's all that you need to know about this type of conservations of momentum, which we call them explosions. And that's the end of the playlist as well. So if you look, I'm going to have a playlist with these 5 lessons on force and momentum, okay? That means that I'll start a new playlist very, very soon. Until then, if you have any questions, let me know directly. Up to then, be happy and healthy. Bye!